Nice to meet you here in person. I'm Ákos Kovács from SZE University, and let me introduce my colleague Tamás Budai, who will hold the second part of this presentation. Our presentation title is Comparison of Different Linux Containers, and in a short agenda we have some discussion of containerization techniques. After that, we present the most commonly used container techniques or containers. After we present some benchmarks, first part some synthetic benchmarks because they are good because we know what we are waiting for from synthetic benchmarks, and then Tamás will be present some real-life application benchmarks as well, and we will show you our results and some discussion and conclusion at the end. First, some discussion of containerization techniques about Linux containers. They called lightweight virtualization as well. I will show you why. It's using mostly the host Unix kernel, host Linux kernels. From the host, it seems as a separate Linux processes only, not a whole virtual machine or whole something like that. And for the biggest advantage, we can use some different distributions, Linux distributions, as well with container technologies. We can see the main difference between virtual machines and containerizations. With virtual machines, we can use different versions of Linux kernel. So if you want to use some application which requires some special Linux kernel modules or something like that, then the virtualization is your solution. But when we use containers, we use the Linux host kernel, and we only have libraries and applications separately. We can see that these are the virtual machines and these are the containers. The VM are bigger, of course. So, the most common Linux containers. The first container is LXC, which is Linux container. It was the worst widely used Linux containers. It is using C groups to limit different things like how much processor unit does we use, or how much memory does we want to use, or limit the I/O and something. The Docker is an extension of LXC containers. It extends special kernel modules to improve the separation of the different containers. But the biggest disadvantage is it uses a server client architecture, so we have to use Docker daemon, which requires root privileges to use Docker in a HPC or on a normal PC. The different Linux containers too is about Singularity. Singularity is intended to use in high PC environments. It doesn't require root privileges, which is a big advantage. It uses the same user inside and outside in the containers. It is compatible with Docker. As we can see, we can import Docker images, which is widely used, to Singularity and use them as native. And we can use InfiniBand and GPU accelerators as well, mostly out of the box. This is the good. Okay, the test system. We use the Huawei Blade servers to test these containerization techniques with Ubuntu hosts, and for that we used two computers, each with the same configuration, and we used 10G Ethernet for benchmarking network performance. Synthetic benchmarks. For synthetic benchmarks, CPU tests were made by Sysbench. It is an industry standard benchmarking tool for CPUs, and network tests with industry standard Hyper-Turf. These are the versions we used. Benchmark 1, the CPU test. The CPU test, we calculate with Sysbench the first 100,000 prime numbers, and the lower is better. So as you can see, the total execution time we have to manipulate the interval of viewing to show the difference between the containers, the virtualization, and the native running as well. So it is more or less than 1% difference between virtualization, containerization, and native running as well. For the network test, there are a little bit difference. We used iPerf tool to see the measurement throughput of the Docker, LXC, Singularity, KVM, virtualization, and native as well. As we can see, Docker and LXC has a little bit decreased performance. To show that, we measured the TCP retransmission rate, which is a network performance limiter, because if we have a lot of retransmission, the one host retransmit a lot of data. For example, Docker and LXC has more than 1020 or 1500 retransmission rate. As you can see, Singularity and native are almost or as well as 0. To see what's happening, we have to understand the networking of the containerization. If we have a bridge networking, which is default configuration for LXC and Docker, we are using a software implementation called Linux Bridge to ensure the container networking reachability. But after we use a host networking configuration, which means that the container injects her own packages to the host networking, then we have the corrected results. As we can see, now we have all the same measurements. We have all the same transmission or throughput in megabytes. As we can see, the retransmission rates are almost 0 or identical to 0 as well. So these are the synthetic benchmarks. And I asked Tamás to show the real-life applications.
Okay, thank you. Well, as Ákos said, we have made some synthetic benchmarks, but is this thing on? Yeah. Okay, then you can hear me. So the synthetic benchmarks showed us where we should start with these containerization techniques, but if you want to have a good impression on how you can actually use it in this project, then it is important to test with real-life data. For this purpose, I have made several tests using Fil++ and the included fluid toolbox. As I was running the lead-driven cavity problem that is also inside this toolbox. I only changed the number of iterations to be reasonable, and so I didn't have to wait weeks to finish of the simulation. Well, to have a good picture, I have tested by running with 1, 4, and 16 MPI processes. So to see how well these containerization techniques can scale with MPI applications. And for the reason Ákos mentioned that bridge networking cannot be used for this purpose because of the big overhead, I used host networking in all setups. So the networking is host in all of these tests. And to have good results, I have made all of the measurements 5 times and then get an average from them. So the most simple setup was the native and single host, meaning you have a host operating system and the Fil++ application running on it natively. Well, it's not a big deal. You can also use Fil++ like this. You can pull it from Docker Hub and use on your own computer. It's not so important, but for a starting point and to have a good point to compare the other solutions, it must be done. So that was the first measurement. Then I measured the same runtime with the same configuration within Docker, and then with the same thing in Singularity, and then compared the results. Well, as you can see, you cannot see the difference, meaning that both Docker and Singularity performed very well when run on a single host. Well, it's not a big deal. We already seen that in some benchmarks earlier, but that was something that must be done to evaluate all these solutions. So It's all fun and games if you have only one host OS and only one container running on that. It's no big deal. Most of the problems arise when you have to use MPI or some interconnect to communicate and run your simulation on multiple nodes. For that purpose, that's why we use 2 nodes to have some tests with MPI. As you can see, I also did the native test like in the first place, but with 2 hosts. I also did the same with Docker. Only Docker, firstly, the Fil++ application running natively on one side and running inside Docker on the other host. And then running Docker on both of the hosts, and then running Singularity on both of the hosts. Well, you may ask, there's something missing here, the native Singularity part. I didn't make that test because when I tested with the native Docker setup and the Docker setup, they showed very, very little differences. So I don't think that it's necessary to measure the Singularity and the native one. It will yield the same results. Well, as you can see on these pictures, it seems like a very easy thing to set up and to do, but the fun begins when this dashed line, the MPI, crosses the borders of the containers. There are some problems that can arise there. But if you overcome those, then you can actually you can achieve very good results with Docker and Singularity. As you can see, similar results, similar things resulted from these measurements. Both Docker and Singularity performed very well with host networking and MPI. It is important to mention that this time I used MPI over TCP, over IP. Most of the time in HPC infrastructures we are using MPI with InfiniBand or such interconnects, and there is the problem with Docker. Docker cannot play very well with InfiniBand, but Singularity can. Well, for a little bit of conclusion, we had very similar results by using synthetic tests and using the MADF Fil++. And we have seen that both Docker and Singularity has minimal performance impact in terms of CPU. So both could be good candidates for the infrastructure. But if you take a step back and see the bigger picture, Singularity can solve many problems we had with Docker and uDocker. I think that Javier and Carlos also can elaborate on that. But with Docker, we have so many problems like different user IDs and such. Singularity solves most of these problems and can be used as a solution for HPCs. So, and also it has simpler image management. We didn't discuss much about the image management today, but I think it is important to note that Singularity operates very, very easy or very simple images. These are basically files, file systems contained in a single file. The big or the good thing about that is that it allows us to create our own image management. We don't have to use Docker Hub or the implement or the included solution that the containerization technique has. We can do our own image management with Singularity. We can decide, for example, if we want to download it via HTTP or via FTP, or we have all the possibilities. So okay, I think that was all from our part. I wanted to shorten it a bit because we are a bit late. Do you have any questions? Well, if you have, we could discuss it later. Okay, thank you very much for your attention.